This is the Chapter 4 whiteboard lecture on crystallization and melting. And this lecture covers PowerPoint slides 39 through 44 and then 50 through 58. In order to create igneous rocks, we first have to melt some solid portion of the earth. So that is how we create magma. Then igneous rocks form when magma cools and crystallizes, and the crystallization is basically creating all those minerals, those silicate minerals that we find in igneous rocks. So melting and crystallization are important for the process of creating igneous rocks, and those two are really the same process, just in different directions. So a good example to use that we're familiar with is water, right? We have water as the liquid and ice as the solid. Water will freeze when the temperature gets below 32. So it hits 32 and goes below, water freezes. Water melts at the same temperature. So not water, ice. Ice melts at the same temperature, 32, when the temperature is going up. So melting and crystallization are happening at that same temperature, and what's different is the direction the temperature is going, whether it's getting warmer or whether it's getting colder. Magma is a little more complex than water, so the process is a little more complex. Water just has one molecule, H2O. Magma, though, we know, can crystallize lots of different minerals, and each of those minerals is basically a different type of molecule. So, a Canadian scientist named Bowen did a series of experiments with rocks in order to try and figure out what was actually happening during the melting and crystallization process. So he took a rock and he put it into a high temperature furnace and began to melt it. But he stopped several times, quickly cooling it, to see which minerals had actually melted and which were still solid. And then, after he had melted it completely, he cooled it back down, but he did the same thing. He stopped periodically to see which minerals had crystallized and which were still molten. So in this way, Bowen figured out what the temperature was for the crystallization and melting of individual minerals. Well, it turns out that all of the minerals we've talked about, all of the silicate minerals, will have melted by the time a magma reaches 1200 degrees C. So all of those silicate minerals will have melted at that temperature. So each individual mineral has a specific melting crystallization temperature. But to simplify things, since this is an introductory class, we're going to group minerals together that have similar melting and crystallization temperatures. So we have those that melt and crystallize at a high temperature, and that includes olivine, pyroxene, and calcium plagioclase. I have a temperature range written down here. I'm not going to ask you to remember that range. You should remember that 1200 degrees C is when all the minerals are melted, and that minerals basically are all solid once you get below this 650 or 600. So high temperature minerals are going to melt and crystallize at these high temperatures. Then we have a group of intermediate temperature minerals, and those are the amphibole and the calcium sodium plagioclase. And then finally, minerals that melt and crystallize at lower temperatures include quartz, potassium feldspar, and the sodium-rich plagioclase. These mineral groupings should look familiar because basically the minerals that melt and crystallize at high temperatures are the same ones we were talking about as being the main components of mafic rocks. And the same is true for the other two groups, right? So felsic minerals, which included the quartz, the potassium feldspar, the sodium plage, those are the minerals that we find in felsic rocks, and those are the minerals that melt and crystallize at low temperatures. So there is a correlation between the compositional term, mafic, the minerals that are in mafic rocks, and high temperature minerals. This graphic is a drawing that illustrates what Bowen found. So it's called Bowen's reaction series, and it basically, a graph is just a drawing. So it takes the data he found and it puts it in a visual way of seeing it. So we have got temperature over here, right? Hot, starting out hot, going down, so cooling. So we've got lower temperatures down here. And then over on the other side, we've got the composition terms that we use. So ultramafic, mafic, intermediate, and felsic. And then in the center, he's got arrows indicating the actual minerals that he found that crystallized or melted, depending on what direction his experiment was going. So these are divided up into two sections. There is this area over here, which is referred to as the continuous series. And then this section over here, which is referred to as the discontinuous series. So in the discontinuous series, we have several different minerals that begin to form and then stop as another one kind of takes over. So again, starting up at the high temperature, we've got olivine. So remember that was one of the minerals that has a high melting crystallization temperature. So if we start at high temperatures with a magma, and we begin to cool it down, we find that olivine begins to crystallize out as we cool the magma down. At some point, pyroxene starts to crystallize out, and then the olivine kind of stops, and we get just pyroxene. Then the amphibole begins to crystallize out. The two of them crystallize out together for a while. Then pyroxene starts, and amphibole takes over. Now, these are all three ferromagnesian minerals, olivine, pyroxene, and amphibole. Biotite is as well. We don't talk as much about the micas because they don't make up a large proportion of the rocks, so they aren't a dominant mineral. But you can see it is also beginning to crystallize out here. So it's called discontinuous because we start and stop different minerals as the temperature of the magma cools. On the other side, with the continuous series, we just have one mineral crystallizing out, and that is the plagioclase. But it has that solid solution. So up here, where temperatures are still very hot, we get a lot of the calcium-rich plagioclase crystallizing out. But down here, where temperatures are much cooler, we have the sodium-rich plagioclase. And here in the center would be that in-between plagioclase. So we can see that these minerals are grouped in the same way that we grouped the minerals when we were talking about the composition of the rocks. So if you have a mafic rock here, you're going to have mostly the calcium-rich plagioclase, right? And you're going to have pyroxene, olivine, a little bit of amphibole. In the intermediate, you're going to have a lot of amphibole, and you're going to have a more in-between plagioclase. And then finally down here at the felsic level, you're going to have all of these very low temperature minerals, the potassium feldspar, the quartz, and the sodium-rich plagioclase. So Bowen's reaction series basically tells us that different minerals crystallize out at different temperatures. At high temperatures, we get certain minerals crystallizing, and as the temperature cools, different minerals begin to successively crystallize out. So the Earth has cooled down a lot in the last 4.5 billion years. So while we have to melt portions of the Earth in order to make magma, we no longer really melt an entire rock. So for instance, if we were melting in the mantle, that ultramafic rock peridotite, we don't completely melt it. Instead, we partially melt it. So if you totally melt a piece of ultramafic rock, then the melt you get would be exactly the same as the rock you melted, right? Which is considered a source rock. But because Earth has cooled down, we don't actually totally melt those source rocks anymore, and instead we partially melt them. So, how do we know what composition our melt is going to be if we're only partially melting the rock? Now, remember, Bowen found that not all minerals melt at the same temperature. So, we're going to partially melt the rock, and some minerals are going to melt and others are not. Turns out we can predict the composition of the magma if we know these two things. The composition of the source rock, so whether the source rock is ultramafic, mafic, intermediate, etc., and the percentage of partial melting. It turns out that the percentage of partial melting for what's happening on the Earth is usually about 20%. So 20% of the source rock is going to melt. So if that's happening, then we are leaving some minerals behind. And the minerals we're leaving behind are going to be the ones that melt at the highest temperature, right? We're not getting the rock all the way up to the highest temperature, that 1200 degrees C, where everything would melt. It's just, we just don't have that amount of heat anymore in the Earth. So we're getting the rock, the source rock, up in temperature, but we're never quite reaching the temperature where we would be able to totally melt those very high temperature minerals. So that means that our partial melt is always going to be a little more felsic than the source rock itself. And this is because some of those refractory minerals are going to be left behind. The word refractory just means hard to melt. So, as I said, we can predict based on the composition of the source rock and how much melting is happening. So if we melt an ultramafic source rock, the magma composition that's produced, and this is just through partial melting, is mafic. If we partially melt a mafic source rock, the magma that's produced is intermediate. And if we partially melt an intermediate source rock, the magma that's produced is felsic. So in each case, we're moving one step more felsic, right? We had felsic, intermediate, mafic, and ultramafic as our categories. So we have the highest percentage of silica in this and the lowest percentage of silica here. So in each case, when we partially melt, we're just moving up one category for the magma that's produced. Ultramafic, you make a mafic magma. Mafic rock, you make an intermediate magma. For an intermediate source rock, you make a felsic magma. So it's pretty easy to remember because it's just one step more felsic. So we're going to go over the slides that talk about how we actually do partially melt parts of the solid Earth. So there are three ways in which we can melt parts of the solid Earth. The first one is decompression melting. So the mantle rock that's underneath the crust is very hot. It's above the melting temperature of all of those silicate minerals we talked about. So it's about 1400 degrees C. But it remains solid because of the pressure of the crust sitting on top of it, right? Whether something melts is both a function of temperature and pressure. Pressure squeezes the atoms together so they cannot move and become a fluid. So if we then remove some of that pressure, which we refer to as decompression, then that will allow those atoms to move. They are already hot enough. So decompression allows partial melting of the mantle rock. We don't have to add any heat. It's already hot enough. So this happens in divergent boundaries. And what we're looking at in this figure is a mid-ocean ridge, right? So that's a divergent boundary or a rift. We have the tensional stress pulling apart here, And that has made the lithosphere and crust in this area here much thinner than it is over here. And that allows this mantle rock to move up. It's under less pressure, therefore, and it begins to partially melt. So this is important in divergent boundaries. And since we are melting the mantle, that's an ultramafic source rock, right? And so we're going to make a mafic magma in this situation. The second way in which we can melt part of the solid earth is by adding water, referred to as wet melting. So when you add water, you're basically changing the chemistry of the rock. Remember, we had those hydrous minerals. So they had a OH group in them. So if we can add water by creating hydrous minerals in the rock, then we've changed their chemistry. Very similar to how we add salt to the roads and you put salt on your sidewalks. Salt water has a different melting temperature than pure water. So when you just have the snow and ice, that's not going to melt until you reach 32, and it's going to remain ice if the temperature is 32 or lower. But when you add salt to water, it will actually stay liquid until you get down into the 20s and teens in temperature. It will freeze at a much lower temperature, and so you can stop the ice from forming until the temperature gets a lot lower. So the same thing is happening here with wet melting. We are changing the chemistry of the rock we're melting, and that means that we don't have to add any heat if we add the water. So we find this kind of melting at subduction zones because we have a lot of water available at subduction zones. So this is a graphic you've seen before from your book. So we have the subducting slab going down here, and it turns out that in this area here, which is blown up here, water gets removed from that uh, ocean floor that's being subducted, and that water works its way up into the mantle rock here and allows it to partially melt. So this is an important aspect of how we end up with these volcanoes along subduction zones. The third method of melting is to simply add heat, right? So that's the easiest way, simplest way, just add some heat. So how do we add heat? We have to have some heat first to add, and this happens in the same place where the wet melting or the addition of water happens. So we looked here at the addition of water, and that's happening, I change colors here, that's happening right down here, right? But then notice this melt goes up here, and then it begins to sit right here at the base of the crust. So here, that hot magma begins to melt the base of the crust. So we're adding heat from the magma that was produced down here. That's where the heat comes from. So from the first magma. And then that melts up here through the addition of heat. So both of these processes are important for creating these volcanic arcs that we find along subduction zones.